A little Garfield cat face. And so the students decide what they want to draw. They were drawing stick people one day. And we make lots of ring patterns. These are ring patterns of protein. Remember ferritin? Each one of these little spheres is an individual ferritin protein. So there's about 15 ferritins connected together in a circle using our nanofabrication methods. This is a three-dimensional sort of a view. So we can make millions. In just a matter of a few hours and a couple simple chemistry steps, we make millions, like 10 to the 9th patterns per square centimeter. So we're making lots and lots of little patterns. And we use these molecules with different lengths of chains. We bind them with silicon groups or gold groups and sulfur groups. We have different ways that we bind the molecules to the surface. I'm going to spare you the heavy-duty detail. I'll show you some more rings. We like to make rings. These are, we call them Jerryos. They look like Cheerios or donuts. The guy who invented this method is called Jerry, so we call them Jerryos. But this is a 1 by 1 micron area, and there's about 30 rings there. We've made it as high a density as about 200 rings per square micron, depending on the size of our patterning method. Sorry for all the acronyms here. These are acronyms for different kinds of molecules. So here's at least 7 different types of molecules that we use, probably up to a couple dozen different types of molecules. We can make rings, we can make like little pores within a film of molecules, and we can put gold nanoparticles and proteins on these areas by adding different molecules and building things from the bottom up. So these are little clusters of little gold nanoparticles. MPC is a gold nanoparticle with a molecule surrounding it, and these are show-off images. Look how many nanoparticles and nanostructures and how perfect and regular they are. So these are, I didn't go through the details. It has to do with chemistry and solutions and mixing things together, but my undergraduates can do this kind of chemistry. We make these ordered arrangements of nanoparticles and proteins for our studies, which have to do with bioassays and measurements of the material properties at the nanoscale. So the final section, I'm wearing your attention out very, very thin here, is nanotheater, and I'm just going to give you some snapshots of a couple of the high-level projects we're doing in my group. So in my research group, these are pretty crystals. They are copper byproducts. So copper, this is a study we're doing with the National Water Quality Laboratory in Cincinnati, Ohio. And my students went there and worked in their laboratory to study what happens to copper when you add water. I mean, that's as simple as it is. Within 24 hours, you begin to see changes on the surface at the nanoscale that have never been seen before, and the EPA is so happy with us. And so why do we care about copper? Because copper pipes, over time the copper dissolves in your water and the pipes are destroyed and you have to replace them. And that's a lot of pipes all through the country that we have to deal with copper corrosion of. But the other bad effect is copper in your drinking water is not good to drink. You don't want to drink too much copper. So they really care a lot about what happens to copper pipes. And so we're helping them develop new studies with AFM to try to learn what we can do to make it so that your copper pipes last longer. Now these are some beautiful molecules. This is the structure of it. It looks kind of complicated. Believe me, it is. They're cobalt to carborane functionalized porphyrins. And they form these beautiful fractal patterns of these crystals. They just, when you dry them on a surface, they form these beautiful patterns. And we can actually kind of take the size of the patterns and look at how they grow over time to produce these beautiful crystals of porphyrins. And that's one of the studies that one of my graduate students work in. Nanofabrication, we're writing with these porphyrin molecules on the surface and making patterns of squares and triangles because we want to study how do those molecules, do they lay flat or do they stand up? Questions like that we're answering in our laboratory and doing reactions, studying the difference in the properties. If they're laying flat, the properties are different than when they stand up. So we're very interested in those kinds of measurements. And here's a pattern, again, where we're studying different head groups produce different kinds of sizes and structures. These are our sulfur here and methyl groups here, and we're doing further studies with that. This is with the physics department with Professor Phil Adams, and he's found a way to make multi-walled carbon nanotubes. MWCNTS. Carbon nanotubes are something that are really small, have really amazing properties. And so that's a very big area of interest in research, and my group has done a little bit of work with that. And finally, with Professor Isaiah Warner and his group, he's making something called ionic liquid nanoparticles. And they have very interesting properties. And the nanoparticles look like spheres, and they're different sizes and shapes. He calls them gumbos. Group of uniform materials based on organic salts. Gumbos is a little bit more fun. They were invented in Louisiana, after all, than ionic liquid nanoparticles. So we're studying gumbos with Professor Warner. And we're studying beta amyloid fibrils. Beta amyloid fibrils look like this. They look like a mesh of strands that are all mixed together. Those have to do with Alzheimer's disease. And I've done a couple of years of research with a very distinguished professor, and we've been studying how to make it so that the fibrils don't form, and then you don't get Alzheimer's. So we're doing studies related to that. And we're doing studies with these polymer films. Electropolymer films are important for making solar cells and energy conversion. So there's this dream of taking polymers and using a polymer coating on your window as the solar cell. So we're doing studies related to special molecules and materials that can convert and harvest sunlight for energy. Very futuristic stuff. It involves these complicated measurements and graphs. I'm just showing them to you, but I won't go into the details. And then, of course, the DNA, back to DNA and the double strands. We're looking at porphyrin, a small molecule binding to DNA. And so our DNA looks like this. You saw some DNA images early. Looks like a spaghetti randomly tossed on the surface. And we're studying where these spots of porphyrins, the little dots, are binding to the DNA molecules. And this is a single molecule study. Each one of these rings is an individual molecule. Oh, and you can't see it very good, but this is the structure of that molecule. So we're doing molecular squares with Professor Maverick at LSU. So the punch point, the take-home message of this talk is that there are many beautiful things to see in our world, and many at the nanoscale that we have not even seen. So many times in my laboratory, we're studying a new system no one's ever looked at before. And it's very exciting. I hope I've shown you some things that you have never seen before. These are my graduate students, photos of my graduate students, ones that have recently graduated. And my new group, Miss Chen Chen is right here, is helping with the demos outside. And these are undergraduates that have been working in my laboratory, Louisiana natives, Joey, Blaze, Treva, Terrence, and Brendan, who just are learning to use atomic force microscopes. Here's Terrence in front of an optical microscope, and Joey's sitting here with the atomic force microscope. And these, hopefully, are some of my future students. Thank the agencies that are giving me funding to do this research, and thank you very much for your attention. And I'll be happy to take any questions if anyone would like.
So how does the probe not either crush or damage the surface that it's scanning? I don't quite understand. I mean, I imagine like a ballpoint pen going across. And
it can. It sure can. Sometimes we tap. Sometimes we can actually image without touching the surface, depending on the type of measurement we want to make. We have exquisite control of the force. And we can use such piconewton to femtonewton forces. And that's the secret trick. Sometimes we coat the tip with a lubricant to make it slide over the surface. But if we do start damaging the surface or scraping or pushing or damaging, we call that lithography. I showed you some. But yes, we have the electronic controllers developed by physicists and engineers is just amazing. We have exquisite control of the force. Any more questions? Even the younger people? When will you be using an atomic force microscope? Maybe pretty soon, I hope. No? Okay. Thank you very much for your attention.